Romina Arroyo from Universidad Nacional de Córdoba, who will speak today about SKT structures on nilmanifolds. Okay, thank you, Romina.
Thank you very much, Adrian, for the presentation. And I would like to thank the organizers for the invitation, for giving me the opportunity to speak. So today, as Adrian said, I'm going to speak about SKT geometry. And this is a joint work with Marina Nicolini, who is also in the audience. I wanted to start with the outline of the talk. First of all, this is the article. You can find the article on arXiv. It's a preprint. It's pretty new. We submitted in January. And I wanted to start with some definitions and known results. And then the idea is to speak about the existence of invariant SKT structures on nilmanifolds. And we will focus in this question. So then I am going to explain all the concepts, but I would like to start with the question. And the question is the following: does a K-step complex nilmanifold with K bigger than 2 admitting an invariant SKT structure exist? We will focus in this question and we will completely answer the question. And then after this answer this question, we'll speak about new examples. I will present a construction that we made with Marina in order to have more examples of SKT structures on nilmanifolds in higher dimensions. So here I'm going to start with the definition of a SKT metric. So here during this talk, we'll be working with Hermitian manifolds. Here M will denote a real differentiable manifold of even dimension, of dimension 2n. And J will be a complex structure. That means it's a 1-1 tensor on M, which satisfies that in every point, the square of this J is equal to minus the identity, and also satisfies an integrability condition that I'm going to explain later. And a metric G, which is compatible with the complex structure J, is SKT if its two fundamental form, so this form, satisfies this equality. That means it's del bar closed. If you don't know anything about these operators, del and del bar are the Dolbeault operators associated to a complex manifold. But if you don't know anything about these operators, no worries, because I am going to give in 2 minutes another characterization of these metrics. And these structures or these metrics are related with a connection which is called bismuth connection. So when you have, in general, when you have a manifold and you have a Riemannian metric, the most natural connection that we use in order to do computations is the Levi-Civita connection. But the Levi-Civita connection, in general, is not necessarily a well connection for a complex structure. So there are better connections. One of them is the bismuth connection. And this is in general, if you have a triple like this, a Hermitian manifold. So there exist many connections which satisfies that G and J are parallel with respect to the connection. That was proved by Gauduchan. But there exists only one which also satisfies that the torsion is a tree-form. That connection is called the bismuth connection. And why this SKT geometry is related with this connection? Because you can characterize the SKT metrics with this condition. So if the torsion tree-form is closed, then the metric is SKT. Okay, so I think everybody is more familiar with this definition. So I am going to use this definition, and the first natural question is, okay, do we know some Hermitian manifolds which are SKT? And the answer is yes, we know a lot of them because the first examples are Kähler manifolds. So Kähler manifolds are precisely the SKT manifolds which satisfies that this tree-form is equal to 0. So we know a lot of examples. And in order to give another examples, which are not Kähler, we have these examples. So every compact complex surface admits an SKT structure. And from these examples, we can see that not every SKT manifold is a Kähler manifold, because here we have primary Hopf surface. So Kähler manifolds are SKT, but not every SKT is a Kähler manifold. Okay. So if you have questions, please interrupt me. So this is the definition of SKT manifolds, but today we're focused on invariant SKT structures on Lie groups. So from now on, G will denote a simply connected Lie group, and the tensors, the complex structure, and the Riemannian metric will be left invariant. And when we are in this setting, because of the correspondence between Lie groups and Lie algebras, and the invariance of the tensors, we can, all the information in the left side can be studied working at the Lie algebra level. So thinking in this side. So I am going to recall a Lie group is a manifold which also has a group structure, and both structures are compatible in the sense that the multiplication and the inverse in the group are smooth. And when you have a Lie group, you can associate a Lie algebra. A Lie algebra is a vector space with a bracket which satisfies two conditions. The first one is skew symmetric, and the second one is an identity which is called Jacobi identity. And if you have a Lie algebra, you also can associate a Lie group. And when these tensors, when you have two tensors here, a complex structure and a Riemannian metric, then you can think what happened with those tensors in the identity. That will give you an endomorphism on the Lie algebra and an inner product in the Lie algebra. And if you have an endomorphism satisfied that the square is minus the identity and some another condition, and an inner product on your Lie algebra, you can construct a complex structure and a Riemannian metric, both left invariant, using the left multiplication in the group. So during this talk, we'll be working all the time on the right side. So I am gonna write which are what is the information that we have. And as I said, this is an inner product on G. We have an endomorphism on our Lie algebra. This is the compatibility between the inner product and the complex structure. So J is orthogonal with respect to the inner product. These two conditions comes from the complex structure. The first one is because the complex structure is an almost complex structure that satisfies this condition, and this is the integrability condition, the relation between J and the bracket on the Lie algebra. And our torsion 3 form in this setting can be computed by this equality, by this formula. And if this triple is a Hermitian manifold, which is also SKT, so we will have this condition that the three form is closed. Okay. And I'm gonna call these triples, so the triples on the right side, SKT Lie algebras. So when we have all this package, all this information, we will call SKT Lie algebras. And we'll be working on nilpotent Lie algebras. So I am gonna recall, or I am gonna give you the definition of a nilpotent Lie algebra. So in general, if you have any Lie algebra, you can consider this series. So these are ideals of G. And the Lie algebra is called nilpotent if there exists some natural number k such that jk is equal to 0. So if the series stops at some point. And we will call that the Lie algebra is k-step nilpotent if jk is equal to 0, but the previous ideal is not. Okay, so in general, when you compute the bracket of G with G, and then with G, and then with G, at some point, this is equal to 0. Okay, so the baby example in dimension 3 is the Heisenberg Lie algebra. As a vector space is this set, upper triangular matrices 3 by 3 with this bracket. This is a nilpotent Lie algebra, and it's a two-step nilpotent Lie algebra because if you compute the bracket of all elements of this kind of type, then you will have some 0 here, some 0 here, and then if you do again the bracket, you will have that this is equal to 0. So this is two-step nilpotent. And of course, as an example, strictly upper triangular matrices with the same bracket also form a nilpotent Lie algebra. Okay, this is just an example. During this talk, we'll be working with nilpotent Lie algebras of even dimension, but these are only examples of nilpotent Lie algebras. So I'm coming back to SKT geometry. So what is known about the existence of invariant SKT structures on nilmanifolds? Well, in low dimensions, there is a classification. Dimension 4 was studied by Madsen and Swan. Dimension 6 by Fino, Parton, Salomon, and dimension 8 by Enretti, Fino, and Bessoni. And they are the classification, so the problem of understand existence of invariant SKT structure is well understood. And in this slide, I wanted to show you two facts about this classification. The first one is that, so in dimension 4, any nilpotent Lie algebra admits an SKT structure. But in dimension 6, so we have this fact that only 4 of 34 nilpotent Lie algebras, so here we have up to isomorphism, only 4 admits an invariant SKT structure. So in general, if you pick a nilpotent Lie algebra, you can ask yourself if they admit or not an SKT structure, and the answer could be yes or no. Only 4 in dimension 6 admits an SKT structure. That is the first observation. And the second one is that in these dimensions, all nilpotent Lie algebras admitting an invariant SKT structure are two-step nilpotent. Okay, and in general, all the examples, all the known examples of nilpotent Lie algebras admitting these kind of structures are two-step nilpotent. So the first natural question is, if you have a nilpotent Lie algebra admitting these kind of structures, are all of them two-step nilpotent? That was our question at the beginning of the talk, and here I wrote again.
Romina?
Yes.
Is there any curve on some fixed nilpotent Lie group?
Any?
Is there any curve?
What do you mean? Curve and
a family, a one-parameter family
admitting
pairwise non-equivalent SKT structures on a
no, there is no.
So only finitely many on each nilpotent Lie algebra.
Yes. Yes.
But what about 2?
What about 2?
2, or it's unique.
No, you can find more than one. So for instance, in dimension 6, happened that if one left invariant metric is SKT, all of them are SKT, for instance.
Okay.
But in a curve of nilpotent, so are you asking about a curve of nilpotent Lie algebras, non-isomorphic?
No. Only one Lie algebra and a curve.
Yeah, that happened in dimension 6.
Structures. Okay.
That happened in dimension 6.
And do you know if it is possible to have bismuth-Ricci flat? That the bismuth-Ricci tensor is 0 in this setting?
I don't know, but I think that is related with Kähler-like, but I don't know.
Okay. Thank you.
Okay, so we have this question. Here we have an nilpotent Lie algebra with a complex structure. K-step nilpotent Lie algebra with K bigger than 2. And the question is if admits or not an invariant SKT structure. And there are some partial results to this question. And the first one was given in this article. So here the authors prove that if you have a triple, which is Kähler-like, that means is SKT plus some condition, that is that the torsion is parallel with respect to the bismuth connection. So it is a class of SKT manifolds with a nilpotent complex structure. I am not speaking about nilpotent structures, but plus some assumption. So then N has to be at most two-step nilpotent, and the structure has to be abelian. And this is the definition of an abelian complex structure. So for this class, they could prove that N is at most two-step nilpotent. So for this class, the answer of the question is no. And then Fino, Tardini, and Bezzoni prove that if you have a triple with an unimodular Lie algebra, and the triple is SKT, assuming that the complex structure is abelian, then the Lie algebra has to be at most two-step nilpotent. Okay, the idea of...
Sorry, Romina, what was the hypothesis on N? It's only on unimodular.
Yes, I didn't write that, but...
Okay, but...
So here, N unimodular, and here they are assuming nilpotent.
Okay.
Yes, I am only focused on the nilpotent case, but of course I cannot mention all the results of SKT geometry, but there are a lot of authors working on the solvable case or the semi-simple case. So all the results that I am mentioning are only in the nilpotent case. But here, yes, you can assume unimodular, and then you will get that N is nilpotent, and it is two-step nilpotent. So, okay, so we want to answer this question, and our main theorem with Marina, it's a complete answer to this question, and the answer is no. No. So this is our main theorem. Any nilpotent Lie algebra admitting an invariant SKT structure is at most two-step nilpotent. And I want to show you the ideas of the proof because, in my opinion, it's pretty easy to follow. It's pretty easy to understand. There are some key steps, but I hope you can understand. If you don't understand anything, please let me know. But the proof of this theorem will be by induction. By induction here on the dimension of N, of the dimension of the Lie algebra. Okay. Of course, if N is equal to 1, so we are working on a nilpotent Lie algebra of dimension 2, that is, the Lie algebra is abelian. So the statement is true. And the So I am going to explain the induction step. And the idea is we will start with an SKT Lie algebra, and we will construct a new SKT Lie algebra related with the initial one in a lower dimension. Okay, that is the idea. And then we can apply the induction hypothesis, and then everything will go in well. Okay. So we will start with an SKT nilpotent Lie algebra, like this. And then the first step of our proof is try to decompose this Lie algebra of the following way. So we will write G as the orthogonal sum of some vector space of dimension 2, which is J-invariant, and some nilpotent ideal, which is also J-invariant. And we can do that because of a result of Salomon. And of course, the idea is try to find an SKT Lie algebra in a lower dimension. So the next step will be to prove that N with the structures restricted to N give us an SKT Lie algebra. Okay, that is the next step. Once we have this, we prove that this is true. So N is a nilpotent Lie algebra because it's an ideal of G. It's a nilpotent Lie algebra of dimension 2n minus 2. Okay. So there we can apply the induction hypothesis, and then we can assume that N is at most two-step nilpotent. That is the idea. But before to do that, I would like to mention that once you have this decomposition, the Lie bracket on G is determined by the following information. So here, in this decomposition, N is an ideal. So the bracket on N belongs to N, okay? And then if you compute the bracket of E1 with some element on N, that belongs to N because N is an ideal. So here, the adjoint, we have the action of A1 on N, and this is an endomorphism on N. And then we also have the endomorphism associated to N to E2. And of course, we can have some bracket between these two elements because this is only a vector space. But the Lie algebra is determined by these two operators. This bracket, so that element on N, and the bracket on N. And this will be important. And now, since N is SKT, because of the induction hypothesis, we can think that N is at most two-step nilpotent. So then N has its center, so we can decompose N as the orthogonal sum of the center and the orthogonal complement of set on N. And thanks to a result from Enrietti, Fino, and Bezzoni, we know that the center is J-invariant. So it's easy to prove that then this decomposition is J-invariant. And why this is important? Because then we can think in this operator as a matrices, so we can complete an basis on N. and we can work with them as a matrices. And when you think that since A and B are derivations, so we know that if this is, so we're thinking here B, and here the center. So the form of these matrices is like this. And we have here a 0 because A is a derivation. And here we are computing what happened with E1 and some element in the center. So that belongs to the center. So there we have a 0. And the idea on the following, or what we need to prove in order to have a two-step nilpotent Lie algebra, is the following. So something is two-step nilpotent if, when you compute this bracket, this is equal to 0. So if you can prove that this guy lies in the center of G, so we will have this 0 that is equal to 0. Okay? So the idea is try to prove that AB and BB are equal to 0. So that is telling us that the commutator of E1 with something in N lies in the center of N, at least. Okay? So that is our goal. But in order to prove that, first one, we prove that these guys are equal to 0. And in this moment, I would like to show you the difficulty of the problem. So I wrote some computations, and here I want to show you, I'm sorry if it's too small, the letter. But remember, something is SKT if C is closed. So the first thing that we need to do is try to compute the derivative of C. And when you compute the derivative of C, C has 3 sums. And when you compute the derivative, you will get 6 sums, 6 summands on each of these sums. So at the end, you are working with 18 summands, and you have to deal with these 18 sums equal to 0. In this case, we will assume that Z is in the center of N. So here we have to deal with 3 plus 3 plus 3 plus 3 plus 3, so 15 summands. Okay? And when you work with them, you can see that you obtain this equality, and then you obtain this equality, which is also pretty difficult to work if A and B are arbitrary. Okay? So the idea is try to prove that this guy is equal to 0, and in this proof, we are proving that these guys are equal to 0. So now I am going to show you how we deal with this condition. And SKT condition is did C equal to 0, and then working a little bit with this we obtain that this thing has to be equal to 0, And then if you compute the sum over a basis on set, a basis on set, so we have something like this, okay? Something like this, and since these matrices are nilpotent, of course, this part is nilpotent, so the trace of this guy and this guy is equal to 0. And here we can use the properties of the trace, and this term will be 0. And then we will have that the sum of the norms of A set and B set are equal to 0. So then this guy and this guy will be 0. But the idea of this part of the slide is try to convince you that to work with these structures is pretty difficult. It's pretty difficult. Okay. Well, then once you have that these two guys are equal to 0, the idea is try to use the condition on the complex given by the complex structure and the inner product and the SKT and the SKT condition in order to have that AB and BB are equal to 0. Once you have that, it's pretty easy to prove that X lies in the center, so everything lies in the center. So then G is two-step nilpotent. Okay, so the idea of the proof. The idea of the proof is pretty easy. Once you have that ideal N, you made some calculations in these two operators, and then the proofs goes well. Okay, and is there any question about the proof? No.
Sorry, who is X in the last line?
Who is, so X is, it's the bracket between E1.
Okay. Okay,
Because,
thank you.
yes, that guy also has to lie in the center.
Okay.
In order to have two-step nilpotent.
Great, thank you.
But the difficulty part is to prove that these two guys are 0. Okay. Now I would like to focus on examples, and this was one of the motivations. So examples were the first thing that we started to think with Marina, and the lackness of examples in higher dimensions motivated us to think in different constructions. This is one of them, so the successful. But again, I would like to explain the difficulties to find examples here. So, first of all, we are working with nilpotent Lie algebras, and we know that the classification of nilpotent Lie algebras is not understood. Okay, from dimension 7, we know that there are infinitely many nilpotent Lie algebras. So there are a lot of nilpotent Lie algebras. So that is the first difficulty, because if you want to have SKT examples, you need to pick your favorite nilpotent Lie algebra, but there are a lot of them. And from dimension 6, we know that 4 of 34 admits an SKT structure. So which one is the best? I don't know. So once
Romina,
in
dimension 6, all the two-step nilpotent Lie algebras admit 1?
In dimension 6?
In dimension 6, yes.
No, only 4 of the 34.
Yeah, but two-step, I mean. Maybe there are only 4 two-step.
No, not all of them.
Okay.
Not all of them. And imagine you pick your favorite nilpotent Lie algebra. So the second difficulty is that you need a complex structure. And of course, the classification of complex structures is not well understood. So you need to endow your nilpotent Lie algebra with a complex structure. And then imagine you have that package. You need to find a Riemannian metric which is SKT, compatible which is SKT. And in this process, there are a lot of conditions. There are a lot of conditions which are linear, but then there are some of them, like the SKT condition, which are not. Is not linear. So it's pretty difficult to find examples in higher dimensions, and we work a lot with Marina using software, and even using a software, it was difficult for us. So that is the reason why we decided to construct, to think in constructions. And the idea is to use the SKT Lie algebras, the non-SKT Lie algebras in lower dimension, and then try to construct a new one of a higher dimension. So we will start with 2 nilpotent SKT Lie algebras, irreducible in the sense that they are not product of 2 SKT Lie algebras of lower dimension. And we will ask this condition. So now we know that any SKT Lie algebra is at most, so the Lie algebra is at most 2-step nilpotent. So here we are working with 2-step nilpotent, so we can decompose the Lie algebra as its center plus the orthogonal complement of the center. And we will ask this condition. And then the idea is try to construct a new irreducible SKT Lie algebra with the same property. And why we want the same property of here? Because the idea is try to apply repeatedly the construction in order to get higher and higher and higher SKT Lie algebras. And the construction is the following. As a vector space, we will have the sum of the first Lie algebra, the second one, and we will add 2 new elements, so a vector space of dimension 2. So at the end, the dimension of this Lie algebra will be the dimension of n1 plus the dimension of n2 plus 2. Okay? Then we need to endow this vector space with a bracket. I don't know what happened, so please do not see from here. And the Lie bracket will be, the Lie bracket on n1 will be the same as the beginning, on n2 the same, and here we will add this bracket, the bracket of Z with W will be the sum of elements with lies in the intersection between the center and the orthogonal complement of the commutator. So there we are using this condition. Okay? and the rest of the brackets are equal to 0. And we will endow this Lie algebra with this complex structure. The structure will be the same in one, the same on N2, and here, yes.
Sorry, hi Romina.
Uh,
One question. So your Lie algebras are not reducible as SKT, but they are reducible as metric Lie algebras, right?
Yes, that's right. So here we use this, taking the elements here like this. That is guaranteeing that is not irreducible as a SKT Lie algebra, but this is reducible as a Riemannian manifold, and also, of course, as a Lie algebra level.
Okay.
Yes.
Okay. Thank you.
So here, the complex structure is like this. Okay. In this part, in this block. And well, the inner product will be the inner product that makes that the decomposition. This decomposition is orthogonal. Is orthogonal. And this, say, if you make the computations, you can see that satisfies all the condition, and this is an SKT Lie algebra with the same property, that we are assuming, and it's irreducible because of this choice. Okay, so now I am going to show you an example, but I'm sure that you you understand. For instance, we will take this 4-dimensional example of SKT Lie algebra you can find in this article of Madsen and Swan. So here the Lie algebra is the Heisenberg Lie algebra plus R. So the commutator is generated in one. Is generated by this E3, and the guide that we can take in the orthogonal complement of the commutator intersection the center will be E4. So E4 belongs to intersection the center. And this is the complex structure, which is abelian in this case. And then we can do the same with this example in dimension 6. So here the element in the intersection of the center of the orthogonal complement to the commutator is F6. Okay, so now we will construct our example. So we will have, as a vector space, we will have N1 plus N2 plus a 2-dimensional vector space. This will be the bracket with this bracket, and also we will add the bracket of these two new elements. And the inner product will be given by the inner product on N1 and N2. So I'm going to show you because it's easier. So here, as a vector space, is from A1 to E4. So we have the first example, then the second one, and we are adding W1 and W2. This is the bracket in the first example. These are the brackets on the second example, and we are adding this one. And then the complex structure is the same in the first example, the same in the second one, and we add only this part. This structure results to be abelian, and the inner product is the inner product satisfying these conditions. So now we have an example in dimension 12, for instance. And then if you want to have an example in dimension 18, so you can do the same with this new SKT algebra plus the first example, for instance. and you can make a lot of examples. So one remark is the following. In our construction, if you start with two complex structures which are abelian, then the new complex structure will be abelian. But if you have that one of them is not abelian, so then the new complex structure will not be abelian. And why this is important? Because all known examples, as far as I know, all known examples of SKT algebras in higher dimensions are abelian. So these are the first examples of SKT structures with complex structure not abelian. And with this construction, we can get examples in any dimension. In any dimension. If you start with two complex structures which are abelian, you are and you applied repeatedly the construction, you will get examples in any dimension which are abelian. And if you take one of them which is not abelian, you will have examples in any dimension which are non-abelian. And I think well, this is my tab, so thank you very much for your attention.
Okay, thank you very much, Romina. Well, very nice talk. And are there any questions or remarks for Romina?
I can do it.
Okay, you can do it. Jorge?
In dimension 6, are there examples of SKT nilpotent with an irreducible? Yes, right?
With this condition, I am sorry. With this condition, there is not. So I didn't mention with this condition. What we couldn't find with Marina, but I think there is no, because the classification. So you need to do some computations in order to understand the classification, and we didn't find any example with this condition. But
no, but I mean irreducible in dimension 6. Maybe the complex Heisenberg is one of them. Or
there are examples irreducible
in dimension 6 and 8.
Yes.
Ah, okay. No, that was okay. So that's maybe a good class to try to classify. I mean, once we have so many examples with your construction, to try to characterize or classify or something the irreducible ones.
Yes.
No, that's just a comment.
Yes, thank you. Yes, you're right.
Well, I have one question. Go ahead, Enrique.
How's maybe I missed something at the end, but so the examples you build, do they occur in families, right? They're not isolated examples, right? You can.
They're isolated. So
Uh-huh.
once you have two, yeah, so we can construct, yeah, we can construct a family of examples, adding, for instance, one parameter here S and one parameter here T, for instance.
Mm.
But we don't know if these examples are equivalent.
Mhm.
So we
But
need,
you can also use a family as N1, and you get families, right?
yes, yes,
So in that case, I mean, as you all know, I only know one question, right? So I ask the same question regardless of the context, right? So I'm trying to figure if these things occur in families, is there a way to pick the best one? Or I mean, this is a condition. Ultimately, this is a condition on special torsion, right? You ask something special about the torsion. Does this mean that these, in some sense, is this a critical condition for some functional, right? What makes this torsion special? No?
I would say solitons, right? There must be solitons.
maybe.
No,
Come
but yeah,
again?
I mean, you
Solitons for what flow?
Pluriclose flow.
pretty close. Yeah.
Ah, okay. So you expect these to be solitons for the pluriclose flow. Is that it?
No, no, no. No, I mean that there is a notion, right? There is a notion of a special, of distinguished, which is pluriclose soliton. But I don't know if the
Yeah, maybe
construction
some of
fulfills.
them in the curve, there is one soliton and that is the special one. Are you saying that, Jorge?
Yes, I think that maybe in dimension 6 and 8, each nilpotent algebra must have a one or finitely many solitons, right? Are there papers about that? I think, don't you have a paper with Ramiro about
Yeah,
that?
we have a paper, but we focus on the solvable, on almost a billion solvable.
Ah.
So there we have explicit examples of solitons.
Uh-huh.
And in the nilpotent case, we only know that the flow goes to these solitons, but we don't know how they are.
Okay.
So I suppose my question fits in sort of at two levels, right? So in which sense are SKTs special, right? Does this emerge from some sort of variation or discussion or stationary
They,
condition, so on? Yeah. And then among them, if they occur in families, how do you choose the even better ones, right? So that's
so there are special, so SKT metrics are special. First of all, in the sense that they are generalizing Kähler geometry. So that is one of the reasons. The second one is that these structures came from physics. I don't know about physics, but they came from physics. Strings, superstrings, I really don't know. But physicians works with these structures. And then I cannot answer your last question. So I don't know if, so I never thought about the questions if in a family if you have a better one. But
so. Yeah,
but
I
so
was trying to think.
the answer for
Right. So I was trying to think if these guys are stationary or critical objects for some variational principle or flow, then one could try and look at the analytic setup around them, right? Study them as special either limit points or of some flows and some PDE, and then that'll be a different way of looking at them. For instance, if they're critical points, then what's the stability profile, right? Can you do a second variation around these objects? And I'm used to finding special torsion, structures of special torsion coming out of some variational principles. So that would be one way. The other way I know, indeed, is solitons as stationary or sort of self-similar, in a way, solutions to some flow. So if you could fit this into some sort of analytic narrative, that would help me sort of see them for
Yeah, so
that's just me.
In the sense of flows. So if you think in the flow which evolves this structure, that flow is the pluriclose flow,
Okay.
and the special metrics are the solitons, as Jorge said.
Cool.
Yes, that is a fact. That is a fact. They are special for that evolution.
Cool. Thanks.
So may I comment something about Enrique's question? I think in this setting, the special among the special, as you say, is bismuth Ricci flat. Okay, which are the fixed points of this generalized Ricci flow. You remember about Jeff Street's talk? And so, but after I asked Romina, I realized that it's impossible here because they have positive scalar curvature. This bismuth Ricci flat. Okay, and so it's impossible to have that on a solvable Lie group. You have to go to the compact homogeneous case if you. But I think that's one answer. Is bismuth Ricci flat is special among solitons.
Cool.
Like Ricci flat is special among Einstein. I don't know, or Einstein among Ricci solitons. Something. Yeah.
Cool. Thanks. That's a nice adaptation. Thank you.
Okay. Any other question or comment? Well, Romina, I wanted to know in which dimension do you have an example of SKT structure with J non-abelian?
In every dimension.
Beginning in 6, maybe?
Okay, so the thing is the following. In dimension, so the classification in dimension 6. Do you want an example?
Yes, one example with a J non-abelian. Well, no, but there is one
in dimension 6. There are examples with J.
Okay, and beginning with that one, you can add other factors, and you get in other dimensions. Okay.
Exactly.
Okay.
More or less, because dimension 6 is.
Yes, you can construct with dimension 6. You can construct dimension 6 plus 4 plus 2.
Okay.
But if you want dimension 8, you have to create another one.
Okay. I see. Okay. Thank you. Well, are there any final questions for Romina? Yes, Rossi?
Yeah, hi, Rossi Federico.
Hi.
I'd like to make a question about the construction. So you basically prove that by induction you can construct all the metric SKT that are two-step. So you can also use this the proof of the theorem to build a new example. I mean, you start with an SKT metric and then you find some derivation that satisfy your assumption. So the question is, you can pick any derivation that satisfy your assumption and you end up with a new SKT Lie algebra, or there are some other assumption and that make this construction unuseful.
Please, Marina, help me with this. Yes, you're right. So if you start with an SKT nilpotent Lie algebra, and then you compute the derivations, and you use the derivations, well, and you take the derivations. All of them will be derivations with these two zeros. You will have an SKT Lie algebra, but you have to check, Marina, you have to check something.
Yes, you have to check that it is, first of all, SKT, and it has something like with compatibility with J, I think, something with that. But
So
the
it's
problem is
not automatic to.
not automatic, no. And also it's a problem, it's not easy to find derivations, right? In order to satisfy, because I don't remember now, but when we were working with that problem, we started constructing examples because we wanted to look for examples that were not two-step nilpotent. We didn't know at that time. And the problem was that with this idea, we had to check Jacobi also. So maybe now that we know that everyone is two-step nilpotent, maybe it's easier. I don't know. We didn't check, I think. But you have to do, I don't know, d square equal to 0, and with many parameters that cannot be easy. I am not sure.
But for instance, the complex,
But here in this slide, the complex structures the complex structure, you need only to describe what happened on the two new direction you had, right?
so for instance, you this is a condition on A and B.
That's given by Jacobi condition. I
That, no, but integrability condition.
Integrability, yes.
So for instance, your derivation has to satisfy this condition. So they are in blocks, but you have some part, maybe. I'm not sure if you have automatically this equality. For instance, you have to check some things. I think so. No?
Okay.
Yes,
Thank
you're
you.
right. It's not automatic.
Okay, thank you. Thank you.
Okay, and well, Viviana's question, maybe it's the last one, so.
Yeah, sorry, just I wanted to add a comment to this of Federico. Maybe I don't know if derivation is the most complicated, but maybe is the compatibility, because when you have when you reduce dimension, you don't only have these two derivations, but also you have to define which is going to be the bracket of E1 and E2, and that X is the one that you need to verify Jacobi, probably, and. Because I think that derivations, since you have 2 0 blocks, maybe anything you put that goes from V to Z. But I don't know. It's very nice construction.
At the end, that X has to lie in the center. So
yes, of course, the idea.
So that is not a problem, in my opinion.
And if you want to do this extension, you don't want that the Lie bracket with E1 and E2 belongs to the center, because it's not interesting. So it was not easy to find new examples with this construction.
And just one, if you could say anything about solvable non-unimodular, are there examples of SKT?
So we have an article with Ramiro.
Okay.
Studying almost abelian SKT structures, and then
there are examples there.
I'm sorry.
There are examples.
Yeah, there are examples, and we characterize. So fixing the complex structure, because of course there is no classification. So fixing the complex structure, we characterize the SKT metrics. And then there is an article from Swan and Freeberg. I cannot pronounce the last name, but yeah, there is another article working with two-step solvable Lie algebras, and they use a construction. Yeah, that's pretty nice.
Okay.
There are
Thanks
results. Yes.
for the talk. Very nice.
Okay.
And the last thing, I
Yes.
remember that when we try constructing these examples with the derivation D, there were a lot of times that instead of creating a new examples 2 dimensions bigger, we had a new algebra reducible. And you are adding something that can break your irreducibility.
Mhm.
So you have to be careful with that also. That's all.
Okay, then, well, I think it's time to thank Romina again. Thank you, Romina.